Hey everybody. Yes. Yeah. Walmersley number. Mhm. Okay, it's 5:30, so let's go ahead and get started today. Good evening, everyone. How's everyone doing today? Tired? Good? Oh, good. Everyone's doing good, I hope. Right? Okay, so we're week 13. I'm good, good. Yeah, thank you. I'm doing good myself. So, yeah, sure everyone's tired and stressed. That's for sure. Right? Okay, so we're in week 13 right now, and so we have a big week this week, at least in terms of deliverables. And so we have a homework that's due this week, and as well as your models for the final project. Okay, and so I've been getting a lot of emails about the about constructing the models, which is good. So I mean, I'm glad that people are working on it. And so first thing I want to do today is I want to go over something that I think a lot of people are kind of having troubles with. Um, and so just to kind of make sure that you guys are doing that part correctly. So I'm going to do that first thing today. Next thing I want to do is I want to go over the homework a little bit. And so specifically, I kind of want to help you guys through problem 3 because I think we kind of left off last week talking about recursion, and so I want to make sure that we finish that up just so that you guys are good to go for the homework. Okay. Because if you've never done recursion before, it is kind of a strange and kind of very disorienting thing, and so I want to make sure that we're all kind of on the same page with that. Okay, and then from there we're going to start a new set of lecture notes, which is on oscillating flow in rigid vessels. Okay, and so over the weekend I kind of took a look at kind of where we have left to go in this class. And I know for the last few weeks, ever since we kind of came back from spring break, it's been it's been kind of intense, and so it's been kind of intense math stuff. And I know it's kind of a lot to parse, right? And so we have one more week of that, and so I want to cover this unit on oscillating flow just because I think it's really interesting. Um, and then I actually had some more kind of mathy stuff planned, but I think I'm going to kind of get rid of that stuff, and then we're going to talk about some other things instead. Okay, so hopefully this week should be the last week where we do kind of the intense kind of graduate level math stuff, and then from there we can kind of return to first of all, I guess focusing on some vascular, but also just learning some more about biomechanics and connecting that to fluid mechanics. Okay. Um, okay. Um, oh, so one announcement I want to make before the class begins. So a lot of people have been asking me this just because I think not all the image data were kind of made equal, and so some image data are kind of easier to work with than other ones. And so if you want to switch your project to something to a different one, you can. I'm leaving that option open to everyone. And so if you're struggling with your current project right now and you want to work with the different image data, then just let me know, and I'm happy to accommodate that. Okay. But yeah, just let me know sooner than later because the deadline's coming up, and it might be hard to kind of crank out that model if you don't have that much time to do it. Okay. Okay. So are there any questions before we get started for today? Okay. All right. So let's go over the homework first. Okay. Let me go ahead and share my screen. Okay. And so this here is the homework assignment. Okay. So let me kind of scroll up so you can kind of see problem 3, sorry. Okay. And so problem 3, what I want you guys to do is I want you guys to compute the resistance, total resistance of a bifurcating vascular tree. Okay. And so kind of a simple example of this might be something like this, where you have a vessel that comes in on the left and it's going to bifurcate. And so remember, when it bifurcates, it's going to split off into 2 different vessels. Okay. And then each of these are going to bifurcate, and then each of these are going to bifurcate from there. Okay. And so here you can see we have three generations of bifurcations, because we have kind of the first generation right here, second generation right here, a third generation, and then, I guess we have 3 bifurcations and 4 kind of generations here. So first generation, second generation, third, and then fourth. Okay. And so what you're going to do is you're going to compute the resistance of this entire tree. Okay. And I want you to do it for a case where you can have up to 12 generations. Okay. Or in other words, 11 bifurcations. Okay. All right. And so the way we're going to do that is, first of all, we need a formula to compute the resistance of a single vessel. And so that's what we have right here. And so we have R is equal to 8 mu L divided by pi. Oh, this should be little r. And so it should be a radius to the 4th power. Okay. So this is back from our one of our very early lecture notes on these things. Okay.
Professor?
Yep. Mm-hmm.
You said you want 11 bifurcations? Yes.
Yeah. So the order for this should be 11. And so I'll show you how to implement that in the code. But it's basically going to be a problem that's going to be virtually impossible to do by hand. And so I want you guys to do it with code and with recursion. Yeah, we'll walk through this one so that you can at least get this one, and then you can apply a lot of the same logic to do problem 4, which is kind of the same thing but with impedance instead of resistance. Okay, and so the way we're going to do this is we're going to work with situations that look like this. And so if we kind of examine a bifurcation just by itself, we know that we have a parent vessel and we also have 2 daughter vessels. Okay, and so the way that we can compute the total resistance of this entire tree is that we can say that the parent vessel right here, vessel 0, this is going to be in series with vessels 1 and 2, where 1 and 2 are in parallel. Okay, and so in order to compute kind of the total resistance or the equivalent resistance for this entire system, the first thing you're going to do is you're going to combine both the daughter vessels in parallel. And so you're going to do 1 over R total is equal to 1 over R1 plus 1 over R2, and then take the inverse of that, and then add this in series with the resistance of the parent vessel 0. Okay. Okay. And you're going to write a MATLAB code to solve this, and kind of a big driving force for this is going to be recursion. Okay. Okay. And so we talked about this last time, but if you've never seen recursion before, I highly recommend that you watch this video. Okay. And so this video will kind of go through just what kind of recursion is in general, and how you can apply it to solve for computer science problems. Okay. But what we're going to do is we're going to use it to apply to solve for the resistance of this entire thing. And so to solve for the resistance for this entire thing, we're going to call a certain function, and we're going to call that function calculate resistance, and then we're going to give it a number. Okay. And so in this case, we have we're going to put the number 3, and the number 3 is going to indicate that we have 3 different bifurcations that we want to do, right? And so we have this first level bifurcation here, then we have the second level bifurcation, and we have kind of the third level bifurcations, and that's all of these guys. Okay. All right, and so the way this works is that we're going to kind of break this up into sub-problems, okay? And so, if we kind of look at this kind of first branch right here, what we can say is that this parent vessel, R0, this is in series with this big branch and this big branch. If we say that each of these branches, we're going to compute a total resistance for that, each of these are in parallel with each other, right? And so, the total resistance is going to be R0 plus the resistance of this subtree plus the resistance of this subtree combined in parallel. Okay, and so it's kind of like an extension of what we have here, but instead of having a single vessel for the daughters, what we have is kind of entire trees that are down here, okay? Right, and what's unique about these trees is that, we can compute the resistance in exactly the same way as we did for this one, right? But instead of calculating it for 3 different levels or 3 different bifurcations, each of these subtrees only have a generation of 2, okay? Right. And then what you're going to do is you're going to implement the code that does this, okay? All right, and so if you open up the code that I have for you on Canvas, you can see that the main thing I want you to implement is in this code, right? And so we're going to start with the files within this folder right here called resistance vascular tree starter. Okay, so you can see that there's two files. Okay, and so one file right here is called generate bifurcating tree. And so this file, you don't have to change anything to this, but the only thing you see here is that we're gonna define the order as 11, and we're gonna call our function here with that order. Okay, and then once we call this function, then we're gonna enter into this section of the code right here, where we're going to perform the implementation. Okay. And so let's kind of walk through just kind of the basic steps together, so that you can kind of implement this. Right? Okay. And so just like I usually do when I give you code to implement, I'm indicating each of the sections that you have to implement with comments called to do. Okay. So you can see there's kind of 3 sections here that you have to do statements. All right. And so first, let's compute this thing called self-res. Okay, and so self-res, this is going to be the resistance of this particular segment, right? And so to compute this, what we need is basically this formula right here. Okay, and so we're going to implement this this formula in the code, right? So let me go ahead and put this over to the right. Okay, just so that we can kind of still see it. Okay, and so you can see here that self-res is going to be equal to 8 times the viscosity, and viscosity is given by this variable right here. Okay, let's go ahead and copy and paste this down. Okay, multiplied by the length. Okay, divided by pi times the vessel radius. Okay, just like that. Okay, all right. And so one thing you'll notice is that the vessel length is given as a vector here, right? And so vessel length is a vector that has 11 elements in it, okay? And so what I want you to do is I want you to, use the length that's characteristic of this order, right? Because each order of vessel basically represents different, a different type of vessel, right? And so an order 11 vessel here, you can see has a diameter of 1.8 centimeters. You compare that to an order 1 vessel, which is much, much smaller than that. Okay. All right, question. Oh, do I have to do vessel radius to the 4th? Yes, I do. Thanks for catching that. Yep. Okay. And so in order to call for the correct length, what we're going to do is we're going to utilize this order parameter right here, right? Because this vessel length here, vessel length vector is a 11 by 1 vector. Right, and we want to call the correct length for this order of vessel. And so we're going to do vessel length at order, and then vessel radius at order as well. Okay. Right. And so that's how we compute the resistance of this vessel segment right here. Okay. Okay. All right, and so that's the first thing, and so that's relatively straightforward. And so we're just computing the resistance of this vessel segment, making sure to use the correct length and the correct radius. All right, so next thing that we have to do in recursion is we have to define our base case, right? And so our base case, I'm giving it to you here. So our base case happens when order is equal to 1. Okay. And so just like we talked about last time, in order to denote the base case, you need to write an if statement for that, right? And so we're going to have if order is equal to 1, okay? And then what we're going to do from here is we're going to, return something that's needed. Okay, and so and if we're at the base case, basically we're at an order 1 vessel. What that means is that we've reached the end of the tree. Okay, and so order 1 vessels are always at the end of the tree. Okay, and so what that means basically is that you know, an order 1 vessel is not going to have any kids. Okay. Okay. And so in these situations where we don't have any kids, what we say is that the total resistance of this vessel segment, this order 1 vessel segment, is just going to be the resistance of that segment, right? And so we don't have to account for any kids. Okay. You in order 1 vessel. All right. And so the way that we can do this in code is we can say that the value that we're returning here, and so we're returning a variable called resistance. And so what we can say is resistance, which is the variable that we're returning, is equal to just the resistance of this self segment, right? And so we can say resistance equal to self res, okay? And that's it, okay? And we don't have to do anything more than that. And then what we can do here is we can add another thing called return. And so return is a special keyword. And so what that basically tells MATLAB is that I'm done in this function and I don't need to do anymore. And then, you know, there's no reason to go on. Okay. And so you need to have this return function in here just to make sure that, you know, we don't go past this. Okay.
Professor.
Yep.
So are you, so the first self-res, that's the very right of that whole tree, right?
So
the
it's
first order is like the very last vessels.
So this right. So that if you're on order 1, and so basically what we're gonna do is we're gonna call this function again, and so that's kind of the point of recursion, is that we kind of call the function over and over again. And so we're gonna start by calling the function with order 11, and so but eventually, you know, what you'll see is that, you know, we'll call the function with order -1, okay? Because as we go along the tree, you know, we start over here. So let's say that this vessel segment is order 11. Then we're going to call the function again with vessel order 10. And then once we call it again, it's going to be 9, 9, and so on and so forth.
Oh, so you're going left to right?
Exactly. Yes.
Okay.
Yes. Yeah. But the base case, so you have to think about the base case. So that's going to be once you reach the end right here. But when you call the function, it goes from left to right. And this is kind of like the stopping condition at the end. And so if you think of recursion as kind of like a for loop where, you know, you're looping over something multiple times, this is kind of like, you know, this kind of tells the program that, you know, I've reached the last iteration of the for loop and I'm ready to leave here. Okay, and so here's where the recursion kind of comes in, because, you know, if we're not on order 1, then we know that we're going to have some daughter vessels, right? And so we have a situation that looks like this, okay? And so the way that we're going to compute the resistance is our resistance here is going to be self-res, right? And so no matter what, we have to add in the resistance of this vessel segment, okay? And so that's basically the same thing as this R naught right here. So self-res is like R naught, okay? And then to this, we're going to add together the daughter resistances in parallel, right? And so we're going to have 1 divided by R daughter 1 plus 1 divided by R daughter 2, okay? And we're going to raise this whole thing to the -1 power, okay? And so this is for every other situation that you have, where you have a bifurcation, you know, and you need to compute the resistance of each of the daughter trees, and this is how you're going to do it, okay? Okay, and so now the question is, how do we compute this R daughter 1 and R daughter 2, okay? And so just like you see from here, and so, you know, if we say that the resistance of this total thing is calculate resistance 3, then the resistance of each of the daughter trees is going to be the same function, but with the order -1, right? And so if we say that R daughter 1, okay, the way that we can compute this is we can recursively call the function, as we say calculate resistance, okay, but we're going to call it with one less order, okay? And so we're going to say that R daughter 1 is equal to calculate resistance at order -1. And then the same thing for R daughter 2, because we're assuming that both daughters, they're twins. And so, you know, we can assume they're the same. right? And so this is the recursive function call right here. And so, by calling this function again, what we're going to do is we're going to enter it into the body of this function again. But, because we have order -1 here, we're going to call it with one less order. Right? And then what this is going to do is it's going to keep calling itself, and keep, the order, -1, -1. Eventually, we're going to go from 11 down to the base case of 1 right here. Okay. And then once we reach the base case of 1, then everything returns, and then we're good to go. Okay. And so if you run this code, actually this is the right one. So let me go ahead and run this one. Okay. Right. And so if you run this code, then then you get a functions that look like this. Okay. And so you should get a variable that counts the number of vessels, and you should have 2047 vessels. You should have a number for the order, and you should have a number here for the total resistance. Okay. Okay. Oh, one more thing. We actually do need to. Oh, okay, I do that already for you. Okay. Yeah. And so I already wrote it. I already wrote the code here to increment the number of vessels, and so you don't have to worry about that. And so this is basically how you do this problem 3 right here. Okay. And so, I want to make sure I walk through problem 3, and kind of explain this kind of recursive call because you're going to need it for problem 4. Okay. And so in problem 4, what you're going to do is you're going to combine basically the knowledge that you have for recursion here together with the algorithm that we talked about last week for how to find the impedance of a vascular tree. Okay. And so once you combine those two things, you should be able to write the code for problem 4. But basically, this is problem 3 for you. That will get you the solution with the recursion all intact. Okay. Okay. So any questions on this? Okay. All right, so hopefully that helped you guys out for that one, because I know recursion is kind of a tough thing even for me still. So this is in the grand scheme of recursions, this one is relatively simple. Recursion problems can get a lot more nasty, but even then, I had to kind of try this one out a few times before I really got it. So hopefully that was helpful for you guys. Maybe you can watch this lecture again as you're doing the homeworks, and then that'll help you out for problem 4. Okay. And so let me go back to my iPad. Cat's eating dinner. Okay, and so the topic for this week's lecture is oscillating flow in a blood vessel. In particular, we're going to look at oscillating flow in a rigid vessel. Okay. And so this is kind of the kind of like what I mentioned at the beginning. This is kind of the last kind of really intense kind of topic that we'll talk about in this class. But it's really kind of the only 2D method that we have, right? And so if we kind of list out all the modeling techniques that we have so far, we can kind of put them in separate bins, right? And so we have 0D methods, we have 1D methods, 2D, and 3D. Okay. And for 0D methods, what we have is LPMs, of course, right? So our circuit models. Okay. And so circuits, it's technically 0D because there's no sense of distance or anything like that. It's just circuits. And so typically we call those a 0D model. Right? On the other end of the spectrum, we have CFD, right? And that's what you guys are doing for your projects. And so computational fluid dynamics is the that's for 3D kind of flow analysis. And then for the last couple of weeks, we've been discussing 1D equations and impedance. And that's, obviously 1D stuff. Okay. And so we don't really have anything for 2D yet. And kind of the real answer for that is, the reason is 2D, it's 2D analysis is kind of in a strange place where it's you know, it's obviously more detailed than 1D. But oftentimes, you know, if you're gonna put in the effort to go from 1D to 2D, you might as well go from 2D to 3D because it's because you gain a lot more in 3D, and it's and you kind of get, you know, a lot more of that. You get more bang for your buck, I guess what you say, right? That's not to say that, you know, you can analyze a lot of really interesting situations in 2D. You know, and 2D I think is the best for visualization, honestly, because it's easy to kind of look at kind of a 2D image and kind of see exactly what's going on. But in reality, you know, there's not that much applications of 2D out there, and so but you know, that's kind of where we're going to be here, right? And so you know, I think what 2D is nice for is it's really nice for visualizing velocity distributions. And so we've kind of seen this a little bit already. And so if you kind of think back to our review of fluid mechanics from the very beginning of the semester, you know, we saw that, you know, if we have steady flow in a rigid vessel, right, what you end up with is a velocity distribution that's parabolic. Okay. And so this was our Hagen-Poiseuille flow. Okay. And this was really nice because, you know, first of all, you know, we could visualize this, and so we can kind of clearly see that it's a parabola. But another nice thing that you can do from a 2D description like this is you can compute the wall shear stress. Okay. And so the wall shear stress is tau is equal to mu du dr evaluated at little r is equal to the big R. Okay, where u of r here, this is the function that we solve for. Okay, and this is something that we've been missing for a while, right? And so you know, in 0D obviously we can't compute this. In 1D, you know, we can't compute this. We can make an assumption, and we can, you know, and we can do an approximation, but it's not quite the same thing. Okay, and 2D, you know, the kind of the big benefit that you get from that is that, you know, you actually can compute this derivative at the wall, and that's going to give you a you know, a wall shear stress value, which is, you know, very, very valuable for these kinds of simulations. Okay, right. And so we've seen this already for you know, steady flow, but you know, we know for sure that the flow in your cardiovascular system is not steady, right? And so we know that, you know, because the heart is constantly beating and pumping blood in every second, the flow in your cardiovascular system is very pulsatile, right? And so it goes up and goes down, right? Goes up and goes down, and it kind of repeats this over and over and over again, right? And so you know, except for kind of a niche, except for kind of very special situations, you actually don't see this very nice parabolic profile all that often in the cardiovascular system, right? And so what we need to do is we kind of need to take this velocity distribution, kind of build on this, and, you know, we want to answer the question of how does this velocity distribution change when we have a pulsatile or oscillating condition, okay? And that's what we're going to answer this week. Okay. Okay. So any questions on this so far? Okay. And so let me write down question of the week. How does velocity distribution how does velocity distribution look like under oscillating conditions? And the reason we want to know this is because we know that blood flow in the cardiovascular system is pulsatile and oscillating in nature. Okay. And so we're not going to get the nice steady parabolic solution that we saw previously. Okay. All right, question. So how do vessels behave when they don't have blood in them? And do they ever not have blood in them? Yeah, no, that's a great question. And so, I think kind of the main ways that people kind of find this out is through cadavers. And so, if you cut open basically a dead person, you can cut out a vessel. And what you see actually is that the vessels kind of shrink in on themselves. And so the reason for that is, because blood is kind of constantly pumping in your body, you have a blood pressure there that's always going to be non-zero, right? And so to kind of make sure that the vessel stays in static equilibrium with that blood pressure that's pushing out, the vessel kind of has to kind of squeeze in on itself just to kind of make sure to kind of contain that blood pressure, right? And so if you remove the blood pressure from that and you remove the blood, then the blood vessel is just going to naturally kind of shrink up on itself like that. Okay, and that's a phenomenon known as pre-stress. And so what we say is that all the blood vessels, there's some element of pre-stress in there because there has to be some structural stress to oppose that blood pressure. Yeah. Okay. All right. And so for this week, we're going to focus on situations where the pressure gradient oscillates with time. And so basically what we're going to say is that the pressure gradient, is going to be some oscillatory function. Okay. All right. And so actually the result for this is actually going to be really interesting because the result is going to be one of the very few known analytical solutions to Navier-Stokes, right? And so if you know anything about Navier-Stokes, it's one of those unsolvable problems. And so it can only be solved in kind of very unique situations. And so this is one of those unique situations where you can actually get an analytical solution to Navier-Stokes in its closed form and everything. So it's nice. The process to get there won't be very nice, but the solution itself will look nice, and you'll kind of see what I mean by that. Okay, and then from this, we're going to get a new non-dimensional number as well. Okay. And so if you think back to your fluids class, you probably are familiar with things like the Reynolds number, things like the Nusselt number, heat transfer, all those different numbers, right? And so pulsatile flow like this has a very special number that governs its behavior, and that's known as the Walmersley number. Okay. And so the Walmersley's number is something that's unique to just pulsatile flow. And so we'll go over kind of what that is, what it represents, and how the solution kind of depends on that. Okay. Okay. And so we probably won't get to the Walmersley number till next time, but I kind of want to let you guys know what that is. All right, question, what is the pressure gradient? Yeah, good question. So the pressure gradient is basically the derivative of pressure that shows up in the Navier-Stokes equation, right? And so if you write out Navier-Stokes, there's always this term that looks like this, right? And so we have partial P, partial Z. And so this right here is the pressure gradient because it represents a change in pressure over a change in distance. And so what you'll see later on in the derivation is that we're going to replace this dp dt with basically a Euler's formula. And so something that's represented by just a generic cosine and sine function. Yeah, and then we'll solve the equation from there. Okay, and so before we jump into the derivation, we have to list out some assumptions. All right. Oh, question. So in steady flow, it's constant. Yes. Yeah. So in steady flow, we assume that the pressure gradient is just a constant down the length of the tube. Yeah. And if you kind of remember when we solved Navier-Stokes back then, we had to assume it's a constant because we have to integrate over it, and then when we integrate, we have to assume it's a constant. Yeah. Okay. And so the first assumption that we'll make is that we'll assume that the artery is sufficiently long. Okay. Next, we're going to assume that the flow is axisymmetric, and so we're going to ignore any changes in the theta direction. Okay. And the last assumption that we'll make is we're going to assume that the walls are rigid. Okay. Okay. And so in other words, we're kind of back to the assumption of kind of a fixed pipe, right? And so, under this solution that we're going to get, we're not going to get any wave propagation phenomenon because you need to have a deformable wall to get wave propagation. But what you'll see is that there's kind of enough math to do under this rigid condition. Okay. And so if you're interested, you can there's a chapter in the course reader that I posted that goes over how to modify this theory for deformable walls. And it's fascinating, but it's also like 20 pages of pure math. And so I'm not going to go over it in this class, but if you are interested, I would highly recommend that you check that out. Okay, so any questions on this so far? Okay, and so if we apply all of those assumptions, and so if we apply all those assumptions, what we get is the Navier-Stokes equations reduces to the following form. And in particular, the z component of the momentum of Navier-Stokes. So we have partial uz, partial t is equal to 1 over rho minus 1 over rho, partial p, partial z, okay, plus nu, partial squared uz over partial r squared, plus 1 over r, partial uz, partial r. Okay. And so this is the equation that results. And so, we still have a partial differential equation here. Okay. And so that's kind of sad because PDEs are not fun to solve. Okay. And so we still have a PDE, but the nice thing here is that this PDE is now linear. Remember last week when we talked about linear functions, right? And so a nonlinear term in this expression would be something like velocity times velocity, or velocity times the derivative of velocity, right? And so we don't have any of that here. And so, we can see that we have velocity terms, but each of the velocity terms here are linear. Okay. All right. And so, you know, what we're going to do today is we're going to basically work on this equation and solve it for, you know, for under certain conditions. Okay. So, but before I do that, you know, let me go ahead and talk a little bit about function decomposition. Because what we're going to do is we're going to solve this equation assuming that the pressure gradient is purely oscillating, right? And so by purely oscillating function, what I mean is a function that looks like this. Okay. And so purely oscillating function will be, you know, a function that kind of goes up and down, just like, you know, a good oscillation. But, you know, it has a zero mean. And so what that basically means is that it's oscillating around a mean value of 0, right? And so if you took kind of the time average of this entire function over a long period of time, what you should get is a mean value of 0. Okay, and so that's what we're going to assume. But, you know, for for cardiovascular flows, and in particular the pressure, we know the pressure it goes up and down, and so it oscillates and it's pulsatile, but it doesn't have a 0 mean. Right, and so in reality, our true function might look something like this. Okay. And so we might have an oscillation, okay, but the oscillation is going around something that's non-zero, right? And so here we can see we have a mean pressure that's way up here. And so the idea with function decomposition is that, you know, since we just want to work with this guy, because mathematically this is kind of the simplest thing to work with, okay, we don't want to have to deal with a mean term. And so what we can say is that, you know, our true function here, it can be decomposed into two things that can be added to each other. Right? And so we take this new function and we add it together to our purely oscillatory one, where this new function is just simply going to be the constant mean. And so if we take a function where the pressure gradient is a constant mean, and then we add that together to a function that's purely oscillatory, okay, then you can get the true function back. Okay? And the nice thing about this is that this constant mean function, we know how to solve it already, because this is our parabolic Poisson flow. Okay. And so once we find the oscillatory solution, all we have to do is just add it together to the steady state solution or the mean solution. And then, you know, we can get the total response for the kind of the general wave, or, you know, the true function. Okay. Okay. But for this class and for the next one, we're going to focus on the case on the right, where we have just a purely oscillating function that just oscillates around 0. Okay. Okay, so any questions on this so far? Okay. All right, and so, you know, assuming that we have a purely oscillatory function, okay, what we can do is we can say that our pressure gradient is a purely oscillatory function. Right, and so what we're going to plug in is we can say that minus partial p partial z, okay, is equal to a, which is a generic constant, times e to the I omega t. Okay. Remember, e to the I omega t, if we plug in Euler's formula, is just a sum of cosines and sines. And so it's a times cosine omega t plus I sine of omega t. Okay. Right, and then we're going to plug. We're basically going to plug this in into Navier-Stokes, okay? Or what remains of Navier-Stokes. Okay. And so if our pressure gradient takes this form, then what we can say is that our solution for the velocity, this is going to be some kind of separable function. Okay. Or in other words, what we can say is that uz, which is a function of r and t, is equal to u of r times e to the I omega t. Okay. Right. And we can assume this just kind of based on the form of the PDE that we have. Okay. And then we're going to take this and we're going to plug this into our Navier-Stokes equations. Okay. And so everywhere that we see a pressure gradient, which is only once, we're going to plug in the above expression, I omega t. Okay. And then whenever we see a velocity, we're going to plug in this expression on the bottom. Okay. We have basically a separation of function, and so we have u of r, which is our our dependency on r, as well as e to the I omega t, which is our oscillatory function with the same frequency. Okay. All right. So any questions on this before we start to plug it in? Okay. All right, so let me write down our Navier-Stokes equations just to kind of remind you. And so our Navier-Stokes equations from a couple pages ago was partial uz partial t is equal to -1 over rho times our pressure gradient, partial p partial z, plus nu partial squared uz partial r squared plus 1 over r partial uz partial r. Okay. Okay. And so let's go ahead and plug in. Right. And then what we get is the following. And so the first thing on the left-hand side, we have partial uz partial t. Right. And so we're going to take the time derivative of this uz term right here. Okay, so we have partial t of u of r e to the I omega t. Okay. Next, we have -1 over rho. And so, we plug in for partial p partial t, our pressure gradient. What we have is a positive a over rho e to the I omega t. Okay. Plus nu times the following. So we have partial squared, partial r squared of uz, where uz is u of r e to the I omega t. Okay. Plus 1 over r partial r of uz, where uz is u of r e to the I omega t. Okay. Okay. And so we plug all those in, and then we see that every single term here has e to the I omega t. Actually, first, let me take the derivative of that first term. And so the derivative of that first term is going to be I omega, okay, u of r, e to the I omega t. Right? This is equal to a over rho e to the I omega t plus nu e to the I omega t. I'm just going to factor that out times d squared uz dr squared plus 1 over r du dr. Okay. All right, question? Let's see. So that thing that's underneath the A, that's rho, and so that's density. Yep. Okay. And so now that we have it in this form, we can see that the e to the I omega t's is going to cancel out everywhere, okay, as it should. All right. And if we take this expression and then we kind of move the terms around a little bit, and we multiply by r squared. Okay. Right. What we get is the following equation. So we have r squared d squared u dr squared, okay, plus r du dr, okay, minus I omega r squared divided by nu times u is equal to minus a r squared divided by mu. Okay. All right. And so this is kind of the midway point right here. Okay. And so we have a bit more to go, but this is kind of an interesting form right here. Okay. And so the things that I want you guys to kind of to notice here is that we're starting to get terms that look like this. And so we have an r squared up here and a dr squared on the bottom, right? And so there's that kind of connection there. We have an r right here and a dr on the bottom, and so there's that connection, okay? As well as, you know, some other stuff, right? But that pattern there, that the fact that we have, you know, those kinds of things matching is going to be key to our solution. Okay. Okay. So any questions on this? Okay. And so in order to make this equation a little bit easier to solve, what we're going to do is we're going to make a change of variables. All right, and so the change of variables we're going to make is we're going to define a new variable called x. Okay. We're going to say that x is equal to I to the 3/2 times r times square root of omega over nu. Okay. And then what we want to do is we kind of want to replace all the r's in our previous equation with x's. Okay. And so to do that, we need to do a little bit of prep work, right? Because not only do we have r's by themselves, but we also have derivatives with respect to r too. Okay. Okay. And so we need to use a little bit of chain rule here in order to convert some of those derivatives from derivatives in r to derivatives in x. Okay. And so let's take the the term with a single derivative first, right? And so that term is r du dr. Okay. And then what we're going to do is we're going to transform that derivative using chain rule. Okay. And then the chain rule gives us the following. And so instead of du dr, what we have is du dx times dx dr. Okay. And so we kind of broke apart that derivative there in order to have a dr on bottom and a dr on top. Okay. Right. And so this term right here is significant because what we have is we have an expression for x up there, right? And so what we can do is say this is equal to, let's see, r du dx times ddr of x. And so x here is I to the 3/2 times r times square root of omega over nu. Okay. So all I did there was just plug in x into that r derivative. And so we take the derivative with respect to r. That's going to cancel out this r here. And so this is equal to du dx times r times I to the 3/2 times square root of omega over nu. Okay. Right. Because I took this, after I took the derivative with respect to r, I just replaced it with another r. Okay. Right. It's like that meme of Mo throwing the drunk guy out of the bar, but then another one just kind of shows up just because he was kind of already there to begin with, right? And so you know, we got rid of one r from the derivative, but we had another one waiting in the wings to replace it. Okay. And this is significant here because this quantity in the parentheses, r times I to the 3/2 times square root of omega over nu, this is this exact same thing as x, right? And so in the end, what we get is x du dx, okay? And this is equal to r du dr. Okay? And so in the end, it comes out really clean. Okay? And the reason it comes out clean is because this change of variables was chosen very carefully. Okay? And so this is nice because now what we can do is we can plug this back into our equation and then eliminate r from that term. Okay. And so all I did on this page was that, you know, for mathematical purposes that you'll see later, we want to replace r with this variable x, okay, because it's going to make our solution a little bit cleaner. And so all we're doing is we're going through the process of replacing the r's in our derivatives. Okay? And so this is the first term, and then we're also going to need to replace the second order derivative term as well. All right, question, how do people figure this out? That's an excellent question that I don't know the answer to. And so I'm partially kidding. So for this one, you know, what we'll see is that the hint that I gave you earlier was that, you know, the fact that we have r squared times a second order derivative and r times a first order derivative here, this looks like a very special ordinary differential equation known as Bessel's equation. And so what we're doing right now is we're doing kind of these special mathematical manipulations in order to get this to look exactly like Bessel's equation, right? And so our goal is kind of Bessel's equation right now. And so we're not quite there because we have some kind of extra stuff floating around, but eventually we're going to get to Bessel's equation. Yeah. But you know, and this is something, and you bring up a good point because this is something that is really glossed over in a lot of classes that have derivations like this. Like someone didn't just sit down and think of this in 45 minutes. Like this was like years and years of work. And so, you know, we're getting like the absolute Sparks Notes version of this. But, you know, whenever you see like a derivation in like a physics class or an engineering class like this, like it was not a trivial thing to come up with. And so, you know, a lot of times, especially for something like this, it seems like a lot of the steps I'm just pulling it out of my ass and say, we're going to do this and it's going to work and it's going to be magic and it's great. But it wasn't like that. And so this kind of method here, this derivation, this was probably the result of of a poor researcher's many years of work. Yeah, so we probably tried a bajillion different things, and this is the one thing that stuck. Yeah, and so what you're seeing is a very polished version of it that in no way represents kind of the work that goes into this stuff. Yeah, it's not the Bezos equation; it's called the Bessel. I'll spell it for you. So it's called Bessel, Bessel equation. Yeah. Yes. Yeah. Michael put it very eloquently. Many teams, many years, much money, and lots of tears. Yeah. Yeah. In fact, yeah, the Michael brought up a good point that it's probably the guy that came up with this. He was just kind of the lucky person that kind of broke through at the end. And so probably before him was a lot of researchers that try to find something significant here, but just kind of came up empty just because it was a really tough problem. But this guy. Not Bessel, but the person who came up with this derivation for this Navier-Stokes equation, he kind of lucked out and he was able to kind of build on the knowledge of a lot of other people. It's like that for research in general. And so whenever you do research, you're building on kind of the shoulders and you're building on kind of the work that other people have done. Yeah. Okay. And so that's the first order derivative term. And so now let's do the second order derivative. Okay. Okay. All right, and so our second order derivative term looked like this. And so we had an r squared, d squared u, dr squared. Okay. And then we're going to convert this. First thing we're going to do is we're going to convert the derivatives. And so this is going to be an r squared, d squared u, dx squared. Okay. And then we have dx dr, okay, times dx dr. Oops, this should be r. Okay. And so we're just going to plug in dx dr twice, okay? And then squared. Because we have x, right? Because x, we know x is this function right here. And so we take the derivative of that, we just get I to 3/2 times omega over nu, right? And so if we square that, what we get is r squared d squared u dx squared times I cubed times omega over nu. Okay. And then, because we were very smart in how we changed these variables, then we end up with d squared u dx squared times, and I'm going to put it like this just to kind of make it obvious. And so we have I to the 3/2 times r times square root of omega over nu, quantity squared. Okay. Right. And because we know that this quantity in here, that this is just simply x, right? And so what we get is x squared d squared u dx squared. Okay. All right. And so if we plug all that stuff in, then we move one step closer to our Bessel equation. Okay. Okay. And so we plug this stuff in. What we get is x squared d squared u dx squared plus x du dx plus x squared u. And this is kind of the main reason we did this, is so that we kind of cleaned up this this term in front of u, okay? And this is equal to x squared a divided by I rho omega. Okay. All right. And so we're close. And so we're not quite there yet, but we're very close. And so what we're going to do is we're going to make one more change of variables, because right now we can't solve this Bessel equation because we have this this guy here on the right. Okay. And so he is our unwelcome guest and we want to kick him out. Okay. And so to do that, we're going to make one more substitution. You've probably seen more change of variables these last few weeks than you probably ever want to see in your life, right? Right. And so the last change of variables that we're going to make is we're going to say that y, and so this is going to be a substitution for u, right? So we like x, and so we want to keep x there, but we want to make a substitution for u this time, right? And so we're going to change from u to this new function called y, and so we have y is equal to u minus a over I rho omega, okay? And this is a relatively simple change of variables because this term on the right, this a over I rho omega, this is just a constant. Okay. And so when we take the derivatives of y, we simply just get the derivatives of u. And so we try dy dx. This is equal to du dx. Okay. And if we take another derivative, so d squared y dx squared, this is equal to d squared u dx squared. Okay. All right. And so that's the last change of variables, I swear. And then after this, there's no more PDE derivation stuff, right? And so believe it or not, we're 2 steps away from the final solution. Okay, so any questions on this? All right. And so if we make that final change of variables right there, what we end up with is this final ODE. We have x squared times d squared y dx squared plus x dy dx plus x squared y is equal to 0. Okay. Right. And so this is this right here is this is what we were looking for from the very beginning. And so now that we've got to this point, we can celebrate because all of our hard work is done. Okay, because this ODE right here is a very special ODE, and this is called a Bessel equation of order 0. And the nice thing about this is, we don't have to do anything because the solution to the Bessel's equation is actually Bessel's functions, right? And so the solution, okay, and so we did all that hard work, and so now we can just say that, Bessel figured this problem out already, and so we're just going to trust him, right? And so we can say that y of x, our solution, is equal to C1 times J0 of x plus C2 y0 of x, okay? Where this J0 here, this J0 here is the Bessel function of the first kind. Okay. And then this y0 here, this is a Bessel function of the second kind. And so on the next page, I'll plot these out for you just so you can kind of visually see what they look like. But this is kind of why we work so hard to get the solution into this form, because these Bessel functions are very well known. You can call them in MATLAB too, actually. So MATLAB has the Bessel functions built in, and it'll just kind of plot it for you. Okay. And so with that said, I'd hate to be this guy's kids because he couldn't come up with a better name than Bessel function first kind and Bessel function second kind. I can only imagine his kids are named first kid, second kid, and that's not a fun proposition. Yeah. Okay. So any questions on this so far? I lived with a guy in grad school who had 2 chinchillas actually, which are very cute. So if you don't know what a chinchilla is, they're basically these rodents, and they're fluffy like clouds. And so it's funny because their bodies are like very itty bitty, but then their fur adds like 3 times the amount of volume, and they're very soft, very skittish, very shy creatures. But so I asked them what they were named. And he said that he couldn't decide on names for them, so he called them the dark one and the light one, because one of them had dark fur and one of them had light fur. And so it was just named like that. And I suggested that we name them Salt and Pepper because they kind of look like salt and pepper, but he didn't want that. He just kept on the dark one and the light one. Yeah. Okay, so let me draw out the Bessel functions for you just so that you can kind of see what they look like. All right, so let me draw J0 first. So this is our Bessel function of the first kind. Okay, and so this is x, and so we'll say this is J0, x up here, okay? And so J0 of x is gonna start out at 1, okay? And it kind of looks like a cosine curve, but it kind of decays with x, right? So it's gonna come up here, it's gonna start up here and go down. Come up like this. It's gonna kind of continue like that, right? It's a little bit shifted up, and so it has a little bit more volume on kind of the upper end of the x-axis, but it goes kind of up and down just like that. Okay. All right, and so that's J0. Let me draw Y0 for you. Okay. And so Y0 looks similar as you get to higher values of x, but the kind of the distinguishing quantity of Y0 is that it has an asymptote at 0, right? And so it's going to start down here, okay, and kind of go like that. Okay? And so the important thing is that as x approaches 0, okay, our function Y0 here, which is our Bessel function second kind, approaches minus infinity. Okay, and so it's kind of like a logarithm function, kind of. It's like an oscillating logarithm. Yeah. Okay, and so I drew these for you here because it's these are very standard functions, and so but the way that people usually use them is that they're mostly tabulated. And so it's not like we can construct these out of like sines and cosines and stuff like that. Think of these functions as kind of the same thing as like sine and cosine, right? And so if you had to describe like sine and cosine to someone, it's not like you can represent that as like an x, like a polynomial or something like that. We just know sine and cosine as sine and cosine, right? And we kind of know what they look like and stuff like that. And so the Bessel functions are kind of the same way. And so they're kind of what I like to think is like fundamental functions that the only way to really describe them is to kind of draw what they look like. But the nice thing is that you can call for their functions in MATLAB, and MATLAB will know exactly what to do. Okay. And so now that we know what the Bessel functions look like, let's go back to our solution here because we're not quite done with the solution because we have these arbitrary constants here, C1, C2. Okay. And so our next task here is to, just like we always do with these differential equations, is to apply boundary conditions to solve for these constants. And so we're almost out of time. So let me just do kind of the first one for you, okay? And so the first boundary condition that we'll set, and so, you know, and I'll say this too, that these are the exact same boundary conditions that we used back in the very beginning of the semester when we were doing steady flow in rigid tubes, right? And so the first of those boundary conditions was we basically required that our solution is finite at the center of the vessel. And so basically, if we evaluate y at x is equal to 0, we should get something that's finite. Okay. And what this tells us that immediately we can say that C2 in our function has to be 0. Okay. Because if we look back on the previous page for the graph of y0, we can see that as x approaches 0, y0 approaches negative infinity, right? And so we can't have that, and so that's a no-no. And so we can't have negative infinity velocity in our blood vessel. Otherwise, you know, a lot of physicists will be rolling over in their grave. And so, you know, the only way that we can have a finite solution is if we say C2 is 0, and so that basically eliminates this entire term right here. Okay. And so we've eliminated this guy from the equation. Okay. And then what we're going to do on Thursday is we're going to apply the other boundary condition and solve for C1. Okay. All right. So any final questions before we wrap up for today? Okay. All right. So that's all we got time for today. So thank you guys for tuning in. Remember to keep working on your projects. You know, work on the homework. And if you're having questions on any of those, you know, please don't hesitate to reach out and ask. Right. So have a great evening, everyone, and I'll see everyone on Thursday.
Awesome. Thank you.
Thanks, guys.
Professor, I have a quick question.
Sure. What's up?
Regarding Silvestre. So I still get those zebra-like models. I know you mentioned that there's a way that we can adjust the I think the graphics card or something. So,
yes. Yeah. Is Isaac still here? Okay. Let me ask the student that that figured that out, and then I'll have him post. I'll give his instructions as an announcement so that you can get rid of that. Yeah.
Sounds good. Thank you very much. I appreciate it.
Mm-hmm. Manuel, do you have any more questions?
Yes, Professor. It's actually for FEA.
Okay. Yeah. Sure. What's up?
It was on the